a series, but it all depends on the response from you guys. So if I were a well-intentioned AI, part 1, group session 180, slides by me. Okay, so Stuart Russell starts out by saying that...
Stuart Armstrong.
Sorry, keep getting confused. Stuart Armstrong starts out by saying that alignment problems are broadly similar, and we can describe them by we approximately specified goals that looked okay, but turned out to be underspecified in dangerous ways. This is, of course, quite similar to Goodhart's law. And because Armstrong has been analyzing Goodhart-like problems for a while, it's unsurprising that he decided to focus on Goodhart's law in this series. So he says that he's going to assume that you have an agent that understands why Goodhart's law is a problem, and it's motivated to overcome it. So it knows that whatever value functions we give it are not the true value function, and it wants to figure out the true value function. And given that assumption, how many alignment problems can it solve? How far can it get? Okay. So, I should mention that his research tends to assume that you encounter scenarios where the AI isn't actually being given rewards directly. So it has to guess what the true reward function is based off just a prior information. So for example, the AI is finished training, now it's chucked out into the world and it's not getting rewards anymore. So it needs to try and infer what the true value function is based off its short period of training. I'll skip Goodhart's taxonomy, but I can go back to it later if anyone wants. So we're going to be pretending that one of us is the AI or one of you is the AI, whatever. So now, sorry about this. Stuart Armstrong examines image classification first, presumably because it's a concrete example. Can't quite say why he chose it, but oh well, it is what it is. So let's just say that AIU suspects Goodhart's law might come into play because, it's called a law for a reason. So it decides to follow along with Armstrong's adaptation of Russell's inverse reward design principle. So Russell said that the designed reward function should merely be an observation about the intended reward rather than the definition, and should be interpreted in the context in which it was designed. This is more or less the same as understanding that Goodhart's law is a problem and wanting to overcome it. So Armstrong said that we can just convert this over to the image recognition scenario and say the labeled examples should merely be examples of the intended category, not a definition of it, and should be interpreted in the context in which they were selected. So from this simple principle, you can infer a few things, like, for example, perhaps there's a lot of different classifiers that I could fit to my data set, and whatever classifier I end up with might not be the be-all and end-all. I should probably explore different classifiers. Or, for example, the humans didn't give an exact specification. Maybe this implies that the idea is too complex or just too costly to give in exact definition. So I should probably be efficient when I'm asking questions instead of barraging them, and so on. These general ideas might also lead to specific techniques, like a way of actually dealing with some image alignment problem. Armstrong uses the idea that there might be many different classifiers that are valid to reproduce something called the background versus semantics idea. And then he looked at adversarial attacks. These problems are just a good fit for the setup, so we'll just go along with his analysis. So let's say AIU encounters distributional shift and adversarial attacks. Just a quick summary, distributional shift is where an AI encounters states or images not in its training set, and so has to extrapolate. So for example, you might be a barbell classifier trained only to detect whether an image has a barbell in it. Perhaps it turns out that all of the images with barbells also happen to have arms holding them, so you just confuse the two and look out for barbells and arms. So this top image is a picture of what sort of features a neural network will focus in on in an image. You can see it's all arms and bells. Adversarial attacks are where a small shift in an image is designed to fool an image classifier into thinking it's the wrong class. Say you're trained to detect pandas, a tiny irrelevant perturbation is made, and you say it's a given. Oh, how'd that happen? All right. Both problems are clearly a result of a lack of information. And we might be able to infer some bits of info ourselves just from the problem setting, but in general, we're going to have to ask humans for more info or just learn more about humans' preferences. All right, so let's say you were trained to detect dumbbells. You are confronted with two images after you finish training. They're unlike anything you've seen in your training set. They both fire up your neurons, and you say, okay, these should both be dumbbells. But the way your neurons are firing up is quite unusual. Both of them seem to be activating very different parts of your network using very different features. Or maybe you were very clever and trained a classifier ahead of time to tell you if images are far from the distribution used in the training set. The point is, it's strange that you have two different images, two very different images according to your network that are both dumbbells. That might imply there's more than one way to classify them correctly. Armed with this knowledge, you train your classifier perhaps a few more times on the dataset you were shown, but in such a way that only one of these images is classified as a dumbbell. By looking at the features they use, or perhaps the activation pattern, you can broadly classify your detectors as being whether they agree image 1 on the left is a dumbbell, image 2 is a dumbbell. Perhaps you say that both images are dumbbells, and so on. Once we made these categories and we've got a ton of models and said, okay, category ones are the models that focus in on the section that we've got in red in this image. That's wrong. Category 2 should be the yellow ones. So they focus in on that section of the image. Category 1 plus 2 is the set of classifiers that focuses on all of the stuff in the purple square. So if you ask a good question, you can rule out whether or not category 1 or 2 or 1 plus 2 are the correct classifiers. This kind of idea is quite similar to the backgrounds versus semantics idea referred to in a paper by Google and DeepMind. In that paper, they say that you should effectively train your classifier to focus in on whatever features are relevant and not any of the irrelevant background patterns. So in our case, the classifier we're using should only use features that appear in images with dumbbells in them. So that it should focus in on the pixels where there's a dumbbell. It should not focus in on blank space. It shouldn't focus in on arms or arm-like features, etc. All of the other things beside a dumbbell should be part of the background. So we got a technique like that. We figured out that, okay, maybe we can ask the human a question to figure out what's going wrong here in this new scenario where we've got images we've never encountered before. Unfortunately, maybe you can't ask the human. So you might just, if you have the ability, give humans multiple classifications by category. Maybe if you can, you'll indicate that you're uncertain instead of giving it a classification. If there's nothing you can do, you might just try and be very conservative. So you might, for example, just say that I'll only say this is a dumbbell if 2 or more or 3 or more different kinds of classifiers agree it is. But without more info or more power, there's not really much you can do. So AIU turns to your other problem, which synergizes with this one, adversarial attacks. On the level of what you can do to solve a given adversarial attack, there's basically the stuff you tried with out-of-distribution images. So creating different classes of models, seeing how they respond, whether there are any that are robust to particular kinds of attacks. So in that case, you might be running adversarial attacks on yourself to try and find out which classifiers are very stable, which are unstable, etc. You might try out different sort of techniques and say, I don't know, you create a distance measure between images to figure out if two images actually are very different under a perturbation. If you say, okay, I'm going to set a cutoff after this distance, if my classifier says that this small change makes a panda into a gibbon, I'll say, no, that's too far. That distance is too great. If not, I'll say, okay, I'll let this perturbation go and I'll accept that this thing is a gibbon. And of course, you can use adversarial attacks to help in detecting out of distribution images and distribution shifts. It's a useful check for when things are unusual. But there's not much else you can do because adversarial attacks depend on the value to be destroyed. And that's mostly a human thing. For example, on the left, you have a panda being perturbed into a gibbon, according to your classifier. And on the right, you have a picture of a cat being perturbed into a picture of a dog. How do you know that the picture of the panda or the picture of the cat that has been changed is not, in fact, a gibbon or a dog? For example, on the left, a human would obviously say, no, that is not a gibbon, that is still a panda. On the right, they might say, well, that's changed enough that it looks basically like a dog, so we'll say that's a dog. But you need human information. You need an understanding of humans in order to solve such questions. And we just don't have that. And unfortunately, without more information about human preferences, we're not going to be able to make much more progress in image classification. This sort of trend will be true throughout the series. The insights will basically be of the form, you're an AI worrying about the gap between your proxy and the true goal, and you have some bit of information about human preferences. What can you figure out from that? And in fact, for general ideas, like, for example, human preferences are fragile, or human preferences are complex, or say, human preferences. Actually, I'm running out of examples. Sorry about that. The point is you need more information either about general human preferences. That can get you quite far. And in fact, Stuart Russell showed in one of his papers that he references in the next week that you can deal with most Goodhart-like effects if you just have a few bits of information about human preference, the general structure. Or you might try and do something that's more area specific, like say, look at, I don't know, playing video games and solving a maze. How can you use the rough information you're given in training to extrapolate and find out new insights to cross the gap between being given a proxy and the true goal that humans want you to aim for? That's the end of this slide, and that's the end of the presentation.